We're ready for 511 we have 1, -1, 1, 1, and let's see what happens here. And so we get that determinant, and so we do 1 minus lambda, -1, 1, and 1 minus lambda. So we put those up, and we're wanting to figure out when this is equal to 0. This gives us 1 minus lambda times 1 minus lambda plus 1 equals 0. I could keep going. Yeah, let's go ahead and keep going, and we can kind of see how this is going to work out. So this will give us 1 minus 2 lambda plus lambda squared plus 1 equals 0. And so we've got lambda squared minus 2 lambda plus 2 equals 0. Okay, you try to factor this, and you fail repeatedly. So what we're going to do is we're going to do the quadratic formula. And by the way, we haven't seen any, but there's no reason that these lambdas have to be whole numbers or integers. You could definitely end up with a situation where you get lambdas that are irrational. They have square roots in them or something like that. And this one's going to be even more interesting than that. So we'll do x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we'll put this one together. Let's put our numbers in there. I guess it's not x, I guess it's lambda. And so lambda equals a positive 2 plus or minus the square root of 4 minus 4 times 1 times 2, so minus 8 all over 2 all over 2. And so lambda equals 2 plus or minus the square root of negative 4 over 2. Maybe you're seeing something interesting. And so lambda is 2 plus or minus. This ends up being 2i all over 2. And if we want to simplify that even more, it's 1 plus or minus I. So what did we get? We got an imaginary eigenvalue. Well, it turns out that we are able to talk about and think about eigenvectors for imaginary eigenvalues, but not yet. So this will show up in a couple videos. So this will be section, let me get the right number so that I don't lie to you. I mean, it's the one titled Complex Eigenvectors. So this will be section 5.5. So in just a few videos, we'll be in section 5.5, and we'll learn what to do with complex eigenvectors and eigenvalues. A real quick observation, though. The reason why is if you go back, if you remember when we rotated things, when our transformations were rotations, we ended up with, I think it was sine theta, cosine theta, negative cosine theta, sine theta. Maybe the sines and cosines were flipped. Okay, but we notice we got one and then the other one, and then that one negative and that one. And you'll notice this is actually a rotation. So this matrix, if we were to draw it as a linear transformation, it rotates. Well, an eigenvector is everything that stays pointing the same direction after the transformation. If everything were to rotate, like say 90 degrees like this, or 45 degrees like this one, if everything were to rotate 45 degrees, then no vector would be pointing the same direction. Everyone would be different. So there are no vectors that point in the same direction, but this complex eigenvector can still have some meaning, and it has a meaning in telling us about this rotation itself. So we'll come and we'll talk about that, and we will make a lot more sense of that in a couple chapters.